In this video, we're going to talk about how we can abstract some of the variables in Cplex to be multiple dimensional variables. And in particular, we'll talk about three of them in a little bit of detail, but there are certainly others that you can use. The ones that we'll sort of chat about are ranges, arrays, and we can sort of put underneath that, this is kind of similar, multi-dimensional arrays. There are also things called tuples in Cplex. We're not going to talk about them, but you can certainly look them up. They're pretty cool. And finally, there are sets, and we'll briefly mention these, especially in the context of arrays. All right. So what we're going to do is we're going to start with this idea of a range. Okay. So what's a range? Well, a range is an increasing set of numbers. And usually we say like 1 to 10 or, 55 to 67. And the way we define a range in Cplex is we use the keyword range. We then provide the variable name. And then we provide the start value. We place 2 dots and end with the end value. Okay. So if you ever want to understand what this notation is, whenever you see the brackets, that means, the sort of like fill in the blank. Okay. So an example of this, we might say, well, I'm going to create a range of values called my dogs, and it's going to be from 5 to 10. Oh, and of course a semicolon at the end. Okay, so my dogs is kind of going to be like a list. So it'll be 5, 6, 7, 8, 9, 10. Okay, so start to end, and it will increment by 1. You can actually do pretty neat things with ranges. So one thing that we can do is we could define a range. So maybe I define a range between 1 and 25. Okay. And I can say, well, I'm going to have a decision variable. That's an integer, x. And it actually has to be in the range IDX. Okay, so that means when I solve my optimization, x is only allowed to be 1, 2, 3, 4, 5, 6, 7, 8, ... all the way up to 25. It has to be one of those integers. Okay, so this is a neat little way that we can use ranges when we're working with our decision variables in Cplex. Now, we can actually do something interesting, which is sometimes we can force the type of this counter to actually be a float. Okay, so right now, these ranges by default are integers. So they're integer values, okay? But we could certainly say something like range float. And I'm just making up variable names. My food equals 10.0 ... to 20.0 semicolon. and then maybe dvars float x in my food. Okay. And again, what that will do is it will ensure that x is of type float as opposed to being of type integer, which is the default. Later on, we'll see that another use of these range variables is to execute for loops. So this is sort of similar to range in Python, if you've ever done any Python programming. This is another usage. Okay, so next we're probably going to move on to something that's a bit more useful in practice, which are arrays. Okay, so arrays are just sort of vectors or lists of variables. Alrighty, so the standard format for defining an array is first we provide the type. So do we want an array of integers, of floats, of booleans? Okay. Next, we provide the name. So this is the name of the variable. Then we provide brackets, and inside we're actually going to give it a range typically. Okay. And then finally we're going to feed it all the values. So maybe there's value 1, value 2, and this goes all the way to value n. And we close bracket and semicolons. Okay, so an example of this would be something like integer, let's say home runs per year. So that's going to be my variable. And let's say we want an array of size 5. Okay, and so we're going to give it a range of 5. And basically what this range does is it allows us to index the array. So really this range is for indexing. So I can say, hey, what's in home runs per year, what's the first element, second element, third element, fourth element, or fifth element? So after that, I just feed in the values. Now, certainly, I don't necessarily have to define an array by using the range 1.5. I could actually provide that range as a variable itself. So this is kind of neat. So I might say something like int n equals 5, semicolon. I then might provide a range called daynum, and that's going to be equal to 1.n. Right. And then finally, I might say, let's get an array of floats, and we'll say calories daynum. And here we'll give, 5 values. So maybe it's 10.3, 6.7, 200, and 72.5. Is that 1, 2, 3? Oh, I'm missing 1. 16. Why not? Okay, so what you can see here is we started with just an integer variable n equals 5. We created a range from 1 to 5, so 1, 2, 3, 4, 5. And then we defined an array of size 5 with index values 1, 2, 3, 4, 5. All right. We can actually use this same idea of arrays to define our decision variables. So before, if we had a set of decision variables x1, x2, and x3, in Cplex we might have written down dvar float plus x1, dvar float plus x2, and finally dvar float plus x3. Okay, so here we have 3 unique decision variables. Okay, but we can actually do this in an easier way. We could just say something like dvar float positive x1 dot dot 3. Okay, and now what we've done is we've used one single decision variable called x that's basically an array of values. All right. We can actually index each one of these values by saying, so if we want to do indexing, we could reference x1, or we could reference x2, or we could reference x3. Okay, and it's a little bit easier to write our optimization programs like this, especially when we're loading in a lot of data, like we'll do in subsequent videos. All right. So I'm going to do a quick example of this in Cplex and how we can have decision variables and regular variables defined using an arrays. In the future, this will naturally lead to loading in large matrices and whatnot, especially like a Q matrix, if you could imagine. Instead of having to type in a whole, matrix, there's going to be fun or algebraic expansions of a quadratic with a matrix. There's going to be fun ways that we can do this automatically. All right, so I'm going to go over to Cplex to show you what I'm talking about. All right, and so what we're going to do is we're going to start by defining a couple float variables. So I'm going to call this my right-hand side. It's going to be an array of size 3, so maybe I have 5, 6, and 10, semicolon. Okay. We're going to create another float called my C. And we'll make this one 2-dimensional. And my C is going to have the values 3 and 2 in it. Right. Next, we're going to define our decision variable. And we're going to say it has to be a positive float. And this decision variable is going to be called x, and it's going to be of dimension 2. So it's going to have like an x1 and an x2 in it. All right, so now let's write our optimization. And so what we can do in our optimization is actually reference these coefficient variables that we've defined above. So maybe I could say my C1 times x1 plus my C2 times x2. All right. I can then write my subject to constraints. Oh, and it looks like I have an error somewhere. Oh, sorry, my C. I missed the C there. What is this now? That looks right. Okay. There we go. So we're going to write our subject to constraints. So maybe I have x1 plus x2 is less than or equal to my right-hand side 1. Okay, and I can repeat this process for all my constraints. So I'm just going to make up a few constraints, and what I'll do is I'll change the right-hand side 1 to indicate the values 5, 6, and 10. So maybe I have 2 times x1 minus x2. Okay, 2 times x1 plus 2 times x2. Okay. So here what we're able to do is you can see we've defined a decision variable with 2 values in it. We can individually reference each one of these values just by using the indexing key 1 and 2. And then we can also reference sort of these variables that we defined that are not decision variables. And so let's go ahead and run this. So I've already added this function to my configuration. That's my default configuration. So I'll go ahead and save it and run. You can see it running. And there we go. And so this is kind of neat. So we see the value of x. It's 3.6666 and 1.33. You can actually also see the data that ended up getting created. So pretty cool. Okay. Now, typically when we're doing indexing, we tend to index using numbers. And specifically uses integers, right? So 1, all the way to n. Okay, so like we had before, we'd use x1, or in the problem we also did like my right-hand side, 3. Okay, so we're referencing or indexing using an integer value. Now, Cplex is actually kind of cool because it allows us to actually index on strings in a set. So let me sort of show you what that looks like. So again, Cplex allows indexing on strings in a set. Okay. So the first thing we're going to do is we're going to create a set, and in this case I'm just going to make it small so that we can sort of plug it into the other problem. All right. So one variable type that we can define is a string, and we're going to wrap it in curly braces. And this curly braces tells Cplex that we're going to create a set that contains a number of strings. Okay, so here I'm going to call this set day of week, or maybe days of week would be better. And it can contain mon and choose. Okay, so just a couple points to note here. Here the quotes are double quotes. Right? So if you use a single quote, it will barf. And again, to indicate it's a set, we actually use the curly brace. So there's a distinction from an array. Okay. All right. We can then define our decision variable. So let's say I'm going to define a float decision variable y, and I can actually index it on days of week. Okay. So if I want to reference a particular value, I can reference y mon. Okay, or y choose. Okay, so this is kind of a nice feature that we can take advantage of. And so you can imagine, let's say you had sets of data, right? Where you could talk about, hey, what's the sum of all my exam grades, right? Or what's the sum of all my homework scores, right? And you can index based on different sets of strings. Okay. So let's sort of do that in Cplex. And we'll just do that by defining a new variable and replacing all the x's with this new variable. Okay, so the first thing I'm going to do is create the string set. So this is days of week. And just to make my life a little bit easier, instead of using mon or Monday and Tuesday, I'm just going to use m and t because I'm just to be a little bit easier. And now what I'm going to do is I'm going to define, again, a float positive. This one's going to be y, and it's going to be indexed by days of week. Okay, cool. Now what I'm going to do is I'm going to replace all the x's with y's, and instead of using x1, x2, I'm going to use ym, yt. Okay, so let's sort of start doing that first. And again, double quotes is the way to go here. And I will change x2 to yt. There. Oh, and I was missing a semicolon there. Okay, so we can go ahead and run this, and you should see we'll get the exact same answer. And we see our decision variable y instead of x because we're no longer using x. And we see days of week here as a set. Now, one interesting thing that I found out about Cplex, which I think is a little bit neat, is if we don't use a variable that we define up here in our optimization, then it doesn't actually give us the values. So I could create a value called, rando number equals 5. Okay, so I've defined that number, but I never actually use it in the program. And what you'll see is when I run it, well, you can see here we get a warning, x has never been used, right? And again, when I run it, rando number, even though it's defined here, does not show up in the problem browser. Now you kind of see it here, but it doesn't indicate any value anywhere that we can find quickly. So just a heads up there. See if we look at the variables. Oh, we're not really seeing anything. Okay, so that's a neat way to sort of index, is using strings instead of numbers. Sometimes it can be a little bit more clear depending on what you're doing. Okay, so it's worth taking just one more step to sort of indicate how we define sets. So even though we used a set here, I'm going to give a little bit more formal expansion on that, and I'm going to actually tell you a couple cool things. So again, the general way is we use curly braces. We then tell it the variable type. We enter in the variable name, whatever we want to call it, and we say that's equal to some set of values. Okay. And there's no rule about, does it have to be an integer or a string? It can be of any type that we've discussed. Also, the neat thing about sets is we don't actually have to pre-size it. So when we were working with arrays, we had to say how big the array was. With sets, we don't actually have to define that. So that's pretty useful. The other useful thing about sets is that they can be constructed through a number of operations. So what do I mean by that? Well, first we'll do a couple example sets, and then I'll show you how we can construct sets using set operations. So we could define a set of integers S1, and maybe that has 2, 3, and 6. We could define a set of floats. Okay, so this is something we can certainly do. Another thing that we could do is we could actually create a set from a range. So let's say we didn't want to type in 1 to 100 as a set. There's actually lots of neat ways that we can create sets. And I'm going to encourage you, again, I'll sort of post this, but there's an OPL language reference guide here that you can sort of go through if you want to learn more about some of these advanced features. Okay, so let's say we wanted to create a set S3 from a range, right? So we already know how to define a range from 1 to 100. Let's say, could we convert it to a set? And certainly we can. So OPL has a function called asSet, and we could just pass it in a range. Okay. As I said, we could actually do set operations. So let's say I wanted to define a set S4, and S4 is going to be the intersection between S1 and S3. And that's a semicolon. Missing them all over. Just assume that I should have a semicolon at the end of each line. It just looks a little bit weird, so I don't write it. And so there's something we could do. So if any set operation that you imagine, so you could append a value, delete a value from a set, you can do the union, the intersection, all sorts of stuff. You can do it. So again, what I'd do is sort of reference the manual, and they provide a list of set operations that you can actually do. So let me see if I can find it. Yeah, so here you can see on page 22 of this one, we have a number of operations: union, intersection, difference, simdiff. You can do the first and last of a set, next, previous, all sorts of things. And there's actually ordered sets and unordered sets, it seems like. I doubt most of y'all will be working with that, but just the idea of sets is probably useful enough. Now, I do want to give one word of warning, which is to say, when you're doing these set operations, so I'm going to do the intersection between S1 and S3. S1 is a set of integers, and S3 is a set of integers, so we can intersect them. If you had a set of floats and a set of integers and you try to intersect them together, Cplex will give an error. So again, you can only intersect similar types, and you can't do these. It seems like you can't do these set operations on different types. All right. So the last thing that we're going to cover are multidimensional arrays. Now, multidimensional arrays are pretty similar to arrays, which is really nice. And they sort of use a similar notation as NumPy in Python by using sort of 2 square brackets. So okay. So how do we do this? So let's say I wanted to define a float variable that was like a 2x3 matrix. Okay. So first I give it sort of this block and indexing that says it's a has 2 rows, right? And then I give it another square brackets and a range, and that will be the number of columns. If I'm going to define it right here, then we basically do I guess, array of arrays, if you want to think about it this way. So here we have 1, 2. 2, 3. And 4, 5, 6. Okay. And so that would give us a matrix A that is 2 by 3. Okay. And certainly we can do similar indexing or referencing. So if we want to reference the ith row, jth column, we would just reference it that way. And again, this is going to be very useful. So if you remember, there were some optimization problems, specifically the blending problem, in which we had a decision variable that was like xij, right? How much of crude oil type I do we put in oil J? And so you can actually use these multi-dimensional arrays to define decision variables that have, multiple dimensions. All right, so, for this one, we could say dvar float plus x. And I think in that problem, there might have been 3 types of crude oils and 3 types of gas that you end up making. So you would just do something like that. And again, it's 2 dots just to make sure. I know I wrote 3 accidentally. And that would create a decision variable that's actually a matrix. So that's pretty useful. More so, not only can you do 2-dimensional vectors or matrices for your decision variables, you can make it, I think, as big as you want. I've only done up to 3. But I'm sure we can do more. So let's say I want to define a decision variable x that's indexed like xijk. So I want to be able to say xij. Actually, let's do 4 dimensions and see if we can even do that. So maybe it's 2 dimensions here. It's 10 dimensions along j, and then 4 dimensions along k, and 2 dimensions along L. All right. You could certainly do that. So I started doing this in Cplex, so you can see I have 1 to 2, then 1 to 5, 1 to 5, and then we could just do one more. Why not? So it's 4-dimensional. And as you can see, it's not giving me an error here. So right now I'm not using that decision variable x in the problem, but you can see it has no problem. So it can accept having a decision variable that has 4 dimensions, and I'm sure you can go to any number of dimensions and it will still work out. Okay, so that's it on multi-dimensional variables, and these are variables that you define on your own, and it also includes the decision variables. All right.